So this is the Berkeley Data Analytics Stack, or BDAS. And as Ben mentioned, you already know a bunch of the things that we've built. We've got Mesos at the lowest level, Alluxio, which used to be called Tachyon at the storage level, and then Spark, which you're hearing about throughout the conference. And these are all projects that were started and finished, and they now have their own open source communities. There are companies behind these and so on. And what I want to do in the rest of my time here this morning is tell you not about what we've done in the past, but about what we're working on now. And that's really on this other side of the diagram. And so as you can see, we're still innovating at a bunch of the different layers in the stack. So I'm going to start bottom up. So at the storage level, we're working on a project called Succinct, which is a system that does very aggressive compression of data, but it allows you to do operations on the data without having to decompress it. So you can squeeze more data into memory, and then you can do all sorts of searches, regular expressions, certain types of calculations on the data without having to decompress it. Succinct also has a knob that lets you tune the amount of compression you do versus how much computation you need to do to answer these queries. And we've got projects going on now to do encryption of compressed data, or compression of encrypted data, actually, compressed graphs, and so on. There's a version of Succinct that's available for download. The URL is on the screen. And everything that I'm talking about in the talk today is available on the AmpLab website. I'll show you the URL at the end of the talk. OK, so that's what we're doing at the storage layer. If you move up a layer, we're working on a system called Velux. So Spark has been quite popular for doing machine learning and for building models. But once you've built your model, you have to serve it. And if you look at applications like the ones I'm showing here, recommendations, fraud detection, Internet of Things, and so on, these applications have requirements that are different than the requirements you typically have for a batch processing engine like Spark. In particular, they have to be very low latency because you're trying to serve predictions when they're needed. They need to be personalized because you have large numbers of users or large numbers of pieces of equipment that you're modeling. And they're happening in an environment that's rapidly changing. So what we're doing in Velux is we're saying, OK, let's take this process of building a model and then serving it, and let's break it into two pieces. So let's break our models into what we call the split processing model. And we're going to divide our machine learning models into a part that works the way machine learning works typically today, which is you look at lots of data, you run large batch processes on a high throughput engine like Spark to compute a model over the entire population. But then we have another part, which is the Velux project, which is aimed at very low latency, very dynamic situations where we have lots of individual small models for the different people or the different entities that we're modeling. And then in Velux, when you need to make a prediction, you query the system. It takes the model that was built in Spark, combines it with the personalized models that was done in Velux, and gives you a low latency personalized answer to your machine learning query. OK, so that's what we're building at the engine level. That's Velux. Moving up from there is another project that Ben mentioned called Keystone ML. And the idea here is to try to make machine learning easier for normal humans. And so the idea is that you want to specify what you want to learn or what you want to predict, but not necessarily how to do it. And if you've used a relational database system, this is the same philosophy that was done in relational database systems, whereas you write a query that says, here's what I want to get out of the database, but you don't tell the system exactly how to do it. The system figures out how to do it. That's what we're doing in Keystone ML. So if you have an operation like a linear solver, in our example here, there's a lot of different ways to do it. The right way to do it depends on what your input looks like. The system could pick the right operation for you at runtime or at compile time. If you have a large pipeline of operations, which most sophisticated applications do now, there's decisions you need to make that you can't look at any individual operation, but you have to look at the whole processing pipeline. For example, what to materialize, what to cache, where to cache it. Keystone ML can make those types of decisions as well. So where Keystone ML is at, we just released a new version this week. The URL is there. We were able to show scale out on multi-terabyte data sets, on order 100 nodes for text processing, speech processing, image classification. We have a bunch of optimizations in there at the individual operator level and across the pipeline. We have a lot of new operators. If you used old versions of MLlib, you'll be happy to see some of the new operators we've put in there. And we're working on even more sophisticated optimizations now in terms of parameter tuning and in terms of automatically choosing what system and how much of a system you need to run your operations on. Okay, so this is Keystone ML.